Alright, here I just want to read a book. I want to read this book on graph theory for a proof of this one statement which we covered in class yesterday as part of the senior course. Let's get to it. Let's see if I can do this without blocking the chat this time. This is the book. It's this book on graph theory by Bing Xiong and some of the Chinese Olympiad people. And I want to cover this result that says, so theorem 2. I wonder if you can see it. Can you see this? So you can't quite see it like this, I know. So you can't see below a certain line for some reason. So I'll just minimize so we see the same thing. Oops. That's slightly annoying. It's about Hamiltonian cycles, okay. Yeah, see, maths takes time. It takes time to even set this silly thing up like that. Of course, you know, if you expect me to edit it all out and just show you the highlights, that's so you can go watch some crap YouTube channel for entertainment. Okay, so G is a simple graph, so I'm assuming that means it has no edge loops. With at least 3 vertices. And for every pair of vertices, the sum of their degrees is more than, or not, at least n minus 1. If that's the case, then it has a Hamiltonian chain. I think this is a result. I mean, we have like Wikipedia Hamiltonian cycle. I think Wiki has a list of sufficient conditions for Hamiltonian cycle. That's similar to Dirac's theorem. With n, if every vertex has degree n over 2 or greater, well, if every vertex, the sum of the degrees is n minus 1 on 2, then at least it's very close, see, because one of them will have to be n over 2. Okay, so we don't really have a name for, let's see, I don't have a name for this result, or it's maybe a nice exercise for us to read it. Okay, so this doesn't even assume it's connected. If there's not enough edges, it'll have to be connected. So alright, we'll first prove that G is connected. Suppose that G contains two or more connected components. Suppose one of them has n1 vertices and another one has n2 vertices. We take one vertex each, v1 and v2, from the two components. So each of their degrees why is it less than or equal to n1 minus 1? So if their degrees are bounded like this, the sum is bounded by this, which is less than n minus 1. Okay. So now why are their degrees less? So being n vertices. Yeah, of course. So they're connected to only the things in their connected component, which is n1 vertices. And you have a vertex already. And it can't loop to itself. So it can only have an edge. Oh, maybe a simple graph also means no double edges. So you can't have two vertices having like 3 edges between them. If that's the case, then of course the degree has to be less than the number of vertices minus 1, because yeah, so if you have like 3 vertices, each vertex can only be connected to the other 2, so the degree has to be less than or equal to 2. Yeah, it's not always equal, because there could be one node that's connected to all of them, each other one's like a leaf. Okay, so that kind of warms us up and tells us what simple means. Okay, now we prove that it exists a Hamiltonian chain. Actually, maybe this is too far left to be seen. We'll go in the middle here. Where's the YouTube thing? It doesn't matter. Okay, now we prove there exists a Hamiltonian chain. The method of proof, in fact, gives us a method to construct a Hamiltonian cycle. Cycle. Suppose G contains a chain from V1 to Vp. Okay. If V1 or Vp is adjacent to one vertex which does not lie in the chain, we can extend this chain to the vertex. Yeah, so even if it doesn't contain that chain, you could even just start it yourself. So you could start at any vertex. It's connected to other something. Go there, and then you look at those 2 vertices. If they're connected to stuff, you can just keep extending the chain. Otherwise, V1 and Vp are only adjacent to vertices of the chain. Okay, so So we do it until we can't do it anymore, okay? So not next to anything else. So it's kind of like, maybe there's a picture down the bottom here, so it's like this chain up to VP, yeah? Okay. Suppose the vertex set adjacent to V1 is all of that. Okay, so there's a bunch of vertices in the chain which are adjacent to V1. And suppose the chain is not the whole graph, the whole vertex set. So P is less than N. Okay, so where's the J1 in that picture? It's not in this picture. Yeah, so V1's connected to well, it's connected to at least V2 and possibly other stuff on the chain. Okay, that's annoying. It's like lagged. If V1 is adjacent to VP, then it's a cycle. Okay. If it's not adjacent to VP. Jeez, what is wrong with this book? If it's not adjacent, I don't want to reload it at the moment because I don't want to waste too much time. Then exists a vertex VL, which is adjacent to V1 and VL minus 1. So that's the picture here. There's a vertex adjacent to V1 and VL minus 1 is adjacent to VP. The internet's not good. Let me just connect to my other internet. Alright, let's reload this page. Okay. Okay, so if it's not adjacent to VP, then it exists a vertex like that, whose previous one in the chain is adjacent to the last thing, which is interesting. So if that doesn't exist, then VP is adjacent to at most. Okay, so VP can only be adjacent to stuff on the chain, so it's at most P minus 1 already. But then there's all the things which are next to the k things adjacent to v1 they can't be adjacent to. So then it's only adjacent to p minus k minus 1 at most. So then you do the degree sum. So k plus p minus k minus 1 equals p minus 1. Yeah, actually these chains, see, if each one is already p minus 1, then 2p minus 2 has to be bigger than or equal to n minus 1. For p has to already be bigger than half of n or something. Yeah, that's good. So there's something like that, and then so even though you can relabel the chain so that I think you can go around to this way up to VP and then back to V1. So now you got a cycle with the same vertices. Cycle with the same vertices. Okay, so if it's not already a Hamiltonian cycle, and G is connected, there must be another vertex V prime which does not belong to the chain and is adjacent to one vertex of the vertices in the chain. Okay. Okay, so here is figure 6.9. It's meant to show us how to extend our cycle. Mm. Hmm. So you do V prime VK. VK plus 1, that's one of them. All the way up to V L minus 1 VP. So you're going right from this picture. This way. Back down. Around to VL. V1, V2. VK minus 1. VK. And then V. It's very strange because we repeat a vertex yet. It's a cycle, but not a Hamiltonian cycle. So what's the point of this now? This seems problematic. It's a Hamiltonian cycle. It cannot repeat vertices, and yet it seems to repeat a vertex. VK. It is easy to see that the condition of theorem 2 about the existence is sufficient, but not necessary. I guess it's trying to say it's easy to say it's not necessary. Suppose G is a polygon with n sides. Here n equals 6. Though the sum of the degrees of any two vertices is 4. Which is less than 5, which is n minus 1 here. G does contain. Yeah, that's all. So that's the sufficient but not necessary, but the sufficiency proof is dubious. How can worry the first? So this does appear to be a Hamiltonian cycle, like no repeating vertices here. Yeah, so your vertex not in the chain, so it's always a different vertex, and you get a cycle. The cycle is pretty big, but if it's the whole thing, it's a Hamiltonian cycle. If it's not, you can. Yeah. So I think we can complete this proof. So we can get a cycle. VK. Yeah, the VK appears twice, that's the thing. Well, that's not what I think. So what I would imagine you do is, because it's a cycle, there's kind of like a symmetry between the starting points. So before you had like V1 to VP, and you couldn't continue it because V1 and VP ran out of adjacent vertices. But the other nodes might not have run out of adjacent vertices because it's connected, right? So they have to be connected to something. And if you make it a cycle, I think what you can kind of do is you can cycle it around to the one that can be continued further and sort of break the cycle there. Continue it further, okay, and then make the cycle again. I think that's a nice way to put it. So maybe that's the way the proof should go. This is not quite what it says here, though, is it? What's it saying here? This picture. It goes to VK. Yeah, I think there exists a chain with n-1 edges. Yeah, I don't know. So this thing is the key idea here. So if this vertex appears at VK, then you have this cycle and you make a VK, basically V1, or VP, sorry, and you relabel it. And then you keep continuing with it from VK. That's where V prime tacks on. And once you can't continue it anymore, you do this little trick here that makes it into a cycle. Okay, that's a pretty neat proof. Hmm. What else is there? There's another one that says this is the one by Orr, 1960. If you have now you have you might also want to check it doesn't work when n equals 3. I guess there's no point when n equals 3 anyway. But did we assume? I think we need more than 3 vertices for this diagram. Okay, if you have this a long proof, we'll have a look. We might not finish it, but we're on a bit of a roll here. G is a simple graph with n vertices for every 2 non-adjacent vertices. So now the condition is non-adjacent. I guess the adjacent one, there's sort of 2 degrees that are wasted. So the non-adjacent ones have a stronger condition. The degrees add up to it's 1 more than what it was before. But the adjacent ones, it's a weaker condition, right? Because it's 1 less than they would have needed. So the adjacent ones really have the adjacent ones seems like it's a stronger condition. It's strange. Now it has to have more edges between non-adjacent ones. Between adjacent ones. Oh, so there's not even a requirement between adjacent ones. So the adjacent ones can just be like degree 2 or something. Maybe that's the key difference here. So it's like a tree or something. Like, what do you call it? Like a linear graph off to one end. That's okay. So if n equals 3, you have to have a triangle because was the other one for cycle as well? It must have been. Contains a Hamiltonian cycle. Why does that change? what am I doing now? It must be a triangle. Because you can't have a tree. Because the non-adjacent ones are degree 1, they're leaves. They don't add up to 3. Okay. Referred by contradiction. Suppose G with n vertices satisfies the condition and contains no Hamiltonian cycle. Well, log G is the graph which satisfies the given condition and the most number of edges. So graph the most edges out of any graph that satisfies this condition. That's so weird. Satisfying this condition. Okay, so the conditions. That's a weird thing to say because if you're just having the most number of edges that satisfies a given condition, then you can get graphs which satisfy the previous conditions, and then those have Hamiltonian cycles. But here you're imposing the condition that the graph does not have a Hamiltonian cycle separately. Very strange. Okay, otherwise G can be added several edges until we cannot add edges. After adding edges, the degrees of the vertices satisfy the condition of degree. Then we get a Hamiltonian chain, contains every vertex of G. We denote the chain V1 to Vn. V1 is not adjacent to Vn. Why is V1 not adjacent to Vn? The same argument if it's a chain but not a cycle. And you get the same way of creating a cycle as before. Where is this condition? So what is the difference between this proof and the other proof? So somehow we got a chain. The degree of the vertices satisfy the condition of degree. So maybe you tried the same proof as before. Okay, what do you do? So you have a bunch of vertices, you start making a chain. You could do that in any graph until you can't get any more adjacent things to the ends of the chain. Okay, and then you have a way to make a cycle out of the chain using the degree condition. So it could already be a cycle, which is nice. Okay, so here this doesn't say it's connected. Well, if you add one edge, it contains this Hamiltonian cycle. Then removing that edge, would that edge be part of the cycle, I suppose, yeah? If you get a Hamiltonian chain, can I just randomly add edges to it? It doesn't seem right. Well, then when you get the chain, you apply the condition, you get a cycle. Then what do you do? Now loss of generality. Yeah, what's with the adding of edges? Keep adding edges to the graph. Okay, so let's look carefully what the statement we're trying to prove is. The G satisfies, so there exists a G which satisfies the condition and contains no Hamiltonian cycle. Okay, so I guess we can take the most extreme version of that. So you keep adding edges. So I guess adding edges preserves the condition of having lots of edges. Okay, so you add an edge, it doesn't do anything. You add another edge, it doesn't do anything. And then you add another edge, it gets you a Hamiltonian cycle. So then you remove that edge, and then you make the argument on that G. That's kind of clever, okay. Do the argument on the G. It's still satisfying these hypotheses. So just adding edges randomly. If you don't have to add edges randomly, you can add edges in a way that builds your cycle. Add edges. So that's where the connectedness is hidden. So you're adding edges to make it connected as well. That's weird, because then you're just saying it doesn't have a Hamiltonian cycle, but it does have a Hamiltonian chain. Okay, so suppose n is greater than 4. So the claim is that all graphs have a Hamiltonian cycle. And you want to, so then you're saying it suffices to prove the graphs with Hamiltonian chains have a Hamiltonian cycle. That's so weird, because, okay, and that's true by the argument we had in the previous theorem. But that doesn't lose generality because you're saying that that is like some sort of maximal counterexample. Oh. Okay, so if you just had a chain without a cycle, that's not possible. So you always have a cycle. When you actually remove an edge, and it still satisfies the conditions, then that actually has a cycle. So actually, once you removed all the edges that you put on, and it still satisfies the conditions, it'll still have a cycle. Okay, so that's how the argument works. Okay, that was interesting. And some examples. Direct. Also nice consequences, we can go from there. Okay. Oh, that'll do for today. Thanks for listening. I do this stuff anyway. It's probably just more interesting if I stream it. People can learn something. Yeah, education isn't always flashy. It's meant to be deep. Alright, whatever. Have a good day. Bye.